Consider a steam power plant operating on an ideal reheat Rankine cycle. The work input to the pump is 20 kJ per kilogram. The work output from the high pressure turbine is 750 kJ per kilogram. The work output from the low pressure turbine is 1500 kJ per kg. The thermal efficiency of the cycle is 50%. The enthalpies of saturated liquid and saturated vapor at condenser pressure are 200 kJ per kg and 2600 kJ per kilogram respectively. The quality of steam at the exit of the low pressure turbine is, so we need to find the quality of steam at the exit of the low pressure turbine in percentage. Let's see the TS diagram of an ideal reheat Rankine cycle. This cycle represents ideal reheat Rankine cycle. So in ideal reheat Rankine cycle, we have two turbines. One is high pressure turbine. So here between process 3 and 4 we have high pressure turbine. High pressure turbine. After the steam exit from this high pressure turbine, it is reheated. It is reheated and the temperature increases, right? So here it's reheated. And from process 5 to 6, we have another low pressure turbine. So here we are having a low pressure turbine. Low pressure turbine. And of course from process 1 to 2 we have the pump. In between 2 to 3 we have the boiler where the steam is heated, and between 6 to 1 there is a condenser where the steam from the exit of the turbine is converted to saturated liquid. Now let's write the information given in this problem. So given info in this problem. So we are given the pump work, right? So let's write pump work as WP, that is 20 kilojoule per kilogram. And the thermal efficiency of the cycle is 0.5. The work done by high pressure turbine, let's write a WT for this. WT high, WTH is equal to 750 kilojoule per kilogram. Also the low pressure turbine work is given, so let's write WTL, that is here 5 to 6. It's given how much it is given, 1500 kilojoule per kilogram. We are also given the enthalpy of saturated liquid. Right? So for saturated liquid enthalpy we write HF, that is given as 200 kilojoule per kilogram. That is at condensed pressure, okay? And also the enthalpy of saturated vapor, that is, let's write Hg for that. This is given as 2600 kilojoule per kilogram. Now let's say X be the quality of steam. Okay, so X be the factor or X be the quality of steam. Quality of steam. So how do we calculate X? Now in order to calculate the quality factor of steam, we need enthalpy at the exit of high pressure turbine. And to calculate that we need the net work done. So for this cycle, net work done is equal to W net is equal to work done by the turbine. Okay, so the high pressure turbine, that is 3 to 4, plus work done by the low pressure turbine, TL, minus the work done by the pump. Now these values are given in the problem, that is work done by high pressure turbine is 750 plus 1500 minus 20. So this value will be, if we do the calculation, it is 2230 kilojoule per kg. Therefore this is the net work done per unit mass. Also we know that the efficiency of the cycle is given. Therefore we know the efficiency is net work done divided by the heat supplied. So for heat supplied, let's write QS. Now eta value is given to us 0.5 and net work done we have calculated, it is 2230. So we can get QS from here. So QS will be 4460 kilojoule per kg. Also we know that the net work done is equal to heat supplied to the system minus heat rejected to us by the system. So net work we know it is 2230 is equal to QS we have calculated 4460 minus QR. So QR we can find from here. QR will be equal to 2230 kilojoule per kg. Now the heat rejected from the system, this occur in process 6 to 1 where the condenser is. So this QR is also equal to enthalpy at 1, enthalpy at 6 minus enthalpy at 1. Now enthalpy at 1, that is enthalpy of saturated liquid HF, and it is given in the problem as 200 kilojoule per kg. Okay, so from here we can calculate enthalpy at 6. So H6 will be equal to 2230 plus 200. So this will come to be 2430 kilojoule per kg. So now we have got the enthalpy at 6 at the inlet of the condenser. Now the quality of steam at lower turbine outlet can be calculated using this formula. So we have assumed it to be X, enthalpy at the exit of the turbine, low pressure turbine, minus enthalpy of saturated liquid divided by the enthalpy of the gas or the vapor minus enthalpy of the saturated liquid. So this comes out to be H6 we have already calculated, 2430 minus, so HF value is given to us, that is 200. Hg is also given in the problem and it is 2600 minus 200. So X comes out to be 0.929. So if we round it off, so it will come around, and we have to find this in percentage, so it will be around 93%. We are just multiplying it by 100 and we are taking only two significant figures. Now let's go back to the problem and fill in the blank. So the quality of steam at the exit of the low pressure turbine is 93%, because we need to round off it to the nearest integer. So nearest integer is 93. Now you should check out the lecture on Rankine cycle with reheat theory and examples on the topic Steam Power Engineering by Professor Vinayak N. Kulkarni of the Department of Mechanical Engineering at IIT Guwahati.